All right. Hey, everybody. Thanks for joining today's nTop Live about how to manage and trace design variations, whether it be for large product families or DOEs. Today, I'd like to show a workflow in nTop platform that highlights some of the versatility that this notebook structure can offer that we have within nTop platform. Now, not only will we be using the concept of variables to drive specific characteristics of a complex structure, but we're also going to be referencing these variables when outputting usable files to ensure that we have distinctive results between them. Now, what we have here is a workflow that already has a generated result on an orthopedic implant, which is an osteo integrative lattice on this tibial tray. In non-medical terms, this is a randomized lattice structure that has been generated on the surface region of just this part. And this part is one of the critical and printable components in a total knee replacement surgery. Now I can open this workflow here, and you can see that this is a custom workflow that has 4 inputs. The first is the lattice design space, which is referring to this thin body region that we plan on populating with the lattice. The second is the strut thickness or thickness of the lattice beams, which is currently set to 0.35 millimeters or 350 microns. The third is a pore size, which is the approximate size of the voids within this randomized lattice. It's currently set to 0.75 millimeters or 750 microns, and it's a characteristic commonly used to represent how porous or empty the lattice is. Now, in the context of orthopedic implants, the more empty the lattice can be, the more your bone can essentially grow into it and grab on tightly. Conversely, you may also want to make sure that the lattice is not too empty, so that the lattice as a whole can maintain structural integrity, with enough beams and with enough material. The fourth and last input is the unique seed down here. And because this block uses a functionality that is based in randomization, the unique seed value ensures that the algorithm will generate a controllably unique result as desired. However, what we want out of this workflow at the end of the day is not just the lattice structure, but we want a printable mesh or an STL file, of the lattice structure itself. So we can use this next block here to generate this mesh. But for the sake of brevity, I'm actually just going to sample just a small portion of this lattice and mesh that instead. And that's going to save us a bit of time for this demonstration. So down here, we have this sampled region of the trabecular structure, and that just looks at this particular region of the lattice, right? So if I just take a visibility on that, you'll see just that sampled portion. And I can drag this sampled trabecular structure into this mesh block. And that's going to work to generate a mesh based on the parameters that I've put in. Just give it a quick second to run. All right, and this is the mesh result here. That looks pretty nice, right? We've got a lot of triangles, so the STL file is going to be a bit on the heavier side, but that's fine because we've captured a lot of the circular nature of these lattice beams. As a final step, we're going to export this mesh out as an STL file, and we have this export mesh block right here. And this block is going to allow us to drag in the mesh that we've just created, as well as choose the location that we want to export it to. Now, normally, I would hit this little folder icon on the right side, designate a location to save, and then have it just save, the STL file out. Easy as that. So actually, let's go ahead and do that now. So I'm gonna hit this icon. I'm already in the folder that I want to save it to, and I'm just going to call it my output mesh and save that as an STL file. That's done. So if I open up that folder, you can see that, this is our output mesh just hanging out in our nTop Live folder. However, there is a bit of a small problem with this approach, right? If I was to, normally this is able to export the mesh out, but if I were to change something upstream, like the input pore size, the entire workflow would regenerate, and you'd create a brand new lattice, and it would resample. But you would actually overwrite the STL file that we've just made, because if you look into the path, you can see that the name output mesh.stpl is essentially hard coded into this block. So what if we don't want that? What if we want to essentially generate a unique STL file for each unique set of inputs that we plug into this workflow, right? How can we make this happen? And the answer there is in dynamically controlling this path that we designate in this export mesh block. Instead of hitting this little folder icon and choosing that save destination, we're going to customize the save destination to recognize new and unique inputs for these design variables, right? So right below, we can see that we have a separate input for directory, and we're going to populate this with the folder name of the location that we want to save this STL to. So I'm going to come up to Windows Explorer, copy that path, and I'm going to paste that right into the directory variable, right? So that's in there. Now, below this, we're going to open up this concatenate text block. And at first, this might look a little bit confusing. But what this block essentially does is that it combines all the components of letters and characters that we see in this list. Breaking this down, we have the directory that we just pasted in. We have a backslash, and then we have the words tibule tray, which is the name of this type of implant, then a dash, then open bracket, the word strut thickness. But right after that, we do see a variable chip here instead of hard-coded text. And this is actually looking at the input strut thickness variable up here, which is marked at 0.35 millimeters. Below it, we have the same setup for pore size, right? The word pore size is hard-coded, and then a reference to the pore size input variable as well. And finally, end with a closing bracket and the STL, the .stl that indicates this file type. So in short, we've essentially broken down the intended save destination for our STL file, basically letter by letter. And where we wanted to dynamically adjust, we've just connected it to the appropriate variables. So let's see this run. I'm going to bring up the intended folder and put that on this half of my screen, and take this nTop file and put it on the other half. Let's just zoom in just a bit. And now I'm going to take the path property of the save destination that we've basically Frankenstein together, right? And I'm going to take this and I'm going to drag this into the path input of the export mesh block. And voila, we can see that the STL file show up just like we wanted it to. And from that concatenated text list that we had, we can see how what we've written has essentially become the formatted text for this file name. And now that it's all put together, we can actually have a little fun with this workflow by tweaking some of the inputs. If we update our strut thickness from 0.35 to perhaps 0.40 millimeters, what we're going to see is that the entire workflow essentially regenerates this new input, right? A new lattice is recreated. That same, square region is resampled. It's remeshed. But this time, the STL file that gets output is going to have a unique file name that now shows that the strut thickness is, reflective of 0.40 millimeters. And that's going to be that new value we plugged in. So once this loading bar clears, we're going to see that STL file quickly export out into the folder. There we go. There's that mesh, and we just saw that STL file show up in our folder. Now, do we want to bump the pore size as well? We can go ahead and do that, right? We can plug in 0.90 millimeters for the pore size value, and we're going to see it again flow through that entire design process that we've created and end up with an STL file that has essentially kept track of that change. In just a few more seconds, and that'll finish. There we go. Mesh is done. You can see that the lattice structure itself is a little bit more sparse because it has a larger pore size. But you can see that on the right side, that 900 micron pore size has now been generated, renamed as a brand new STL file. So essentially, the days of having to save a file with a unique name every single time you do something new, they're essentially over, right? With this method, there's no more accidentally overwriting what you've already made. Won't lose track of what inputs you've already explored if you're doing a large DOE. And there's times when you're just mind-numbingly repeating the same process over and over again on something like a different sized part, like on this tibio tray. So just a few minutes of upfront work to put something like this together, it really enables a new level of automation that can minimize risk, reduce human error, and all in all, just make life easier. And this has a lot of implications when it comes to traceability, because even though this is a really cool idea, traceability doesn't just fundamentally live in the file name. Sure, this approach can be leveraged in a really convenient way to know what file is what. But in a future nTop Live, we can go over another way to dynamically use these variables in a more concrete way, such as using it if in a report format, uh, something like a text file or a JSON file. All right. So if anybody has any questions regarding this, please don't hesitate to throw them at me now. I hope that this has been interesting and perhaps it'll inspire you to maybe start dynamically keeping track of your own design changes using a method like this, or even developing a method of your own. Obviously, what I've shown here today is not intended to be a be all end all solution when it comes to keeping track of your design variables, but this has just been a showcase of what nTop can offer as a general design platform to create solutions that work for your specific applications and your specific needs. So I'm just going to give it a quick second to let those questions roll in. And we'll just give it an extra minute just to see if anybody's still typing. All right, so that just seems to be it for today. I want to thank you all for showing up to our nTop Live, and I hope this has been insightful. Look forward to seeing you again soon. Thank you.